And it's my true pleasure today to welcome a very long friend of our department, Bob Budnitz. And in particular, it's my pleasure to welcome him because he won an award, the American Physical Society Niels Lizard Award. And as part of this award, his mission is to give 3 lectures, right? That's correct? And so it shows Berkeley as one of these three lectures. So it's our pleasure and honor to have him with us today. Bob has mainly been involved with nuclear reactor safety and radioactive waste safety, with one emphasis being on seismic safety. A member of the National Academy of Engineering, he remains active after having retired in 2017 from the University of California, Lawrence Berkeley National Laboratory. Prior to 2002, he had a consulting practice in Berkeley, California for over 20 years. And from 78 to 80, he was at the U.S. Nuclear Regulatory Commission as Deputy Director and then Director of the NRC Office of Nuclear Regulatory Research. He was also the Technical Coordinator of the NRC Special Inquiry into the 79 Three Mile Island accident. He received a bachelor from Yale in 61 and a PhD from Harvard in 68. Please join me in welcoming Bob.
Thanks. In all these years, I've never given this colloquium, although I've sat out there, I don't know how many dozens of times. And I've got a little bit of a hoarse voice, but I'll talk through it. And it's a pleasure to be here. We've been in Berkeley. I showed up in Berkeley as a postdoc at the lab in 1967, and you can calculate my age from that. It's a long time ago. But as he said, as Max said, after about a dozen years, I had a one-man consulting engineering practice most of my adult life. And at the end of my life, I went back to Livermore for 3 years and then to the LPL where then I retired. And the purpose of this talk is to try to explain to people who don't know much about this particular area of engineering why we have confidence that nuclear power plants are safe against earthquakes. You nuclear engineers do a lot of work on all sorts of other issues having to do with nuclear power plant safety, but the field of earthquake safety is a narrow specialty of its own. And the reason it's a narrow specialty of its own is because it calls on expertise that has nothing to do with nuclear engineering. It calls on civil engineering, it calls on seismology, and it calls on a whole lot of what I'll call systems analysis, which is of course nuclear engineering too. But there isn't much nuclear in this, and I'll try to explain why that is. I'm going to start out. Let's see if this works. Yeah. I'm going to explain why we have the confidence that we have that these plants are safe. I have to start out. I'm going to look at the screen here so I can see it. I'm going to start out by saying, what does it mean to say that the design is adequate? The design might be adequate for you and not for you. It might be adequate for the state of California, but not for federal government, that sort of thing. Then I'm going to explain how the design process works. That's the guts of the talk. But you know, besides designing, we have to do analysis in order to understand what you've designed and how it works and how it's going to be safe enough. So then I go on to say I'm going to explain how the whole overall complex system can be designed so it works as a whole, because it has to work as a whole. When you have an earthquake, it has to respond as a whole so that the plant remains safe. So let me go on. There's a crucial thing here that I have to spend a few minutes explaining to you. And that is, whoever owns this thing has to decide which endpoint is required to be safe. And the endpoint is different for a building like this than it is for a refinery, than it is for BART, than it is for a nuclear power plant. And I'll describe that just presently. I'll describe it. You see, a building like this, I'm talking about Echeverry Hall, or if you live in an apartment building, it's designed to assure that after the earthquake of concern, and I'll talk about that in a minute, life safety is preserved. This building is designed, your apartment building down under Berkeley, is designed to assure life safety is preserved. That's in the code. But there's no provision in the code for a normal building like this that the building should function afterwards, never mind that it be, intact. That's just not part of the code for buildings. Okay? So the question is, one endpoint is its life safety for the occupants, and that's a building like this. Another one is it has to function afterwards, even though there might be some small damage. There's a stronger code for hospitals, for the BART system, for the Bay Bridge, and for critical facilities like fire stations, because after the earthquake of concern, they have to function afterwards. And so the code is stronger for them than it is for a residence or an office building. And then there's an even more stringent code to which nuclear power plants are held. And that code says that after the earthquake of concern, which I'm going to talk about in a minute, the thing has to be totally elastic. That is, you have to be able to go look at it, and you can't tell the earthquake happened yesterday. I mean, I'm not talking about a little bit of paint scraping off or something like that, something little. But it basically has to be totally elastic. And that's even a more stringent standard. And the owner of the facility has to decide which one of these is. Of course, in our case, it's not the owner, it's the Nuclear Regulatory Commission, who then tells the utility, PG&E if it's in California, Diablo Canyon, how to design it so that the endpoint of concern is what it is. Oops, hold on. I gotta figure out what I got. Now, the owner also has to decide how big an earthquake they're talking about, which comes down to how frequently it comes around, or if it's a stationary Poisson, how frequently it comes around, or else it comes down to the annual probability that you'll have this earthquake. So, is the earthquake of concern something that might come around every 100 years, or about 1 in 100 this year? Or is it 1 in 1,000? Or is it something lower? Well, I can tell you that for a typical building like Etcheverry Hall, or the apartment buildings in Berkeley, it's designed for an earthquake that comes around every few hundred years, or a few times 10⁻³ per year. Doing it as if it was a stationary Poisson process where it's the same probability every year. That's the typical every few hundred years is the design basis for most of the buildings, the public buildings that you know about. And for the hospitals, it's stronger by a factor of 2 or 3, so it comes around every 1,000 or 2. And the same thing for the fire stations and for the Bay Bridge and for the BART system, because you want them to function afterwards, but also you want them to survive even a bigger earthquake than the one that you're designing for a building like this. Okay. Now, here's how nuclear power plants are designed. The code and the requirements of the Nuclear Regulatory Commission, and this is true all over the world, everywhere in the world, in Russia and in India and in Afghanistan, if they had a reactor, which they don't, but if it was Argentina and they do, the choice that is made by the Nuclear Regulatory Commission is that the nuclear power plant has to be totally elastic with no discernible damage after the earthquake, and the earthquake that is of concern is selected to be slightly less than 10⁻⁴ per year. Or if it's stationary Poisson, comes around every 10,000 years, but it might not be stationary Poisson. So the seismologists have to work out what the likelihood is of earthquakes of different sizes at your site. And the nuclear power plants are designed, the design basis is around or just slightly less than 10⁻⁴ per year. And at that earthquake, the thing has to be totally elastic. Everything that matters. That's the most stringent design of anything around. The big bridges aren't designed for that. Okay, they're designed for something slightly less, but it's a lot. And I just want to tell you that. And who chose that? The Nuclear Regulatory Commission. But if you owned a refinery, you might choose that too, even though you might not be held to it by regulation. So one of the most important things that you have to do when you get started, let me go. There it is. All right. That's the totally elastic, no discernible damage, nuclear power plants. How often? Less than 10⁻⁴ per year. Okay, that's the nuclear power plant. And then the next challenge is to determine what we call the seismic hazard, which is what is the earthquake environment around here? Because the earthquake environment here at Etcheverry Hall is different than it is at Stanford. Heck, it's different than it is, in Oakland, because it's highly local around here. So if you have a nuclear power plant and it's on a site, Diablo Canyon near San Luis Obispo, or maybe it's in Illinois, or maybe it's in New Hampshire, you have to identify, here's how you go about it. You have to identify all of the nearby seismic sources. It's right there. And characterize each one. Now, it's easy at Echeverry Hall because there's one great big fault right here. It's called the Hayward Fault. It's right here. Just goes through the stadiums right nearby. But for a place that has several faults nearby, you have to identify each one of the nearby seismic sources, and the seismologists do this, they have to characterize each one. How do they characterize it? They have to understand how big earthquakes could be and with what frequency, because the big ones come less commonly than the small ones. They develop what's called a seismic hazard curve to do that. And then once you've identified the fault, or maybe it's 3 faults, and the earthquake could here or here or here, it could be a big one or a medium-sized one. For every one of those earthquakes, the seismic energy has to propagate from where the earthquake was to the site. And the site might be 5 kilometers away, but it might be 50 kilometers away, or it might be something in between. And so the seismic energy has to be propagated by analysis from the earthquake source. And by the way, if it's a fault, it might be a line source, it might be 20 miles, okay, to the site. And then you have to understand how the energy gets into the site. Now, that turns out to be based not just on analysis, but a heck of a lot of data. I'll just give you the example. Even in the East, there are magnitude 0s and 1s all the time, little earthquakes. And you can measure how the energy goes from there to here, because you've measured the source and you can measure over here. And so those measurements tell you the attenuation of the motion. It might attenuate by a factor of 2, depending. It might change its frequency. It might start out with a heck of a lot of 10 hertz motion, and that gets absorbed more than the 1 hertz motion, so that by the time it gets to you, the frequency spectrum of this energy is different than how it started. All of that has to be done by analysis so that the analyst has a spectrum based on both the probability and the likelihood and the size of the various kinds of energy, earthquake energy, that get to the site. Okay, now it's at the site. It comes into the building. There are site effects, local site effects. Maybe it's all soil, and then right where you are, it's rock. It changes the frequency. There are various inhomogeneities that have to be measured, and they are measured using these techniques that I mentioned. And then the next part of it is you have to propagate the energy into the structure. The energy comes, the earthquake is coming to you, and there's a base mat, or as you very halt, it's the basement. But we're on the 3rd floor. There are models and measurements that benchmark those models that enable the analyst to tell you what the motion's going to be on that pump that's on the 3rd floor of the turbine building, or what the motion is of that electrical switchgear that's in the yard. Because those motions at the local site where the equipment is, or where the structures are the motion that you have to understand in order to figure out whether the object is going to survive the earthquake. So there's a lot of analysis that goes into what we call the seismic hazard, starting out with identifying the earthquakes, the sources, and the different sizes of earthquakes that might occur and the frequency with which they might occur, and then how the energy propagates to the site and changes its frequency and its amplitudes and that sort of thing. So, by the way, some energy gets amplified and some gets damped. The site effects, the local site effects and that sort of thing. And then propagating inside the structure. And finally, you're standing next to a big heat exchanger on the 4th floor of the reactor building. And if the earthquake occurs over there, we can work out with some confidence, but there's also some uncertainty, what the motion is at that particular thing that you're worried about. And all of that is done in a very, very complex analysis. It's expensive, difficult, requires several different disciplines. It requires seismology and geology and other earth sciences, but crucially it involves a whole lot of mechanical engineering and some other kinds of civil engineering disciplines to work all that out. But in the end, we end up with knowing what the motion is for earthquakes of different kinds, from different sources, different sites, in this very elaborate analysis at the site and then at the equipment. Now, I haven't got time. I could have to give you a whole lecture to go into it in detail. But this is a typical seismic hazard curve in which this is a spectral acceleration. I seem to remember that this is 10 hertz, but there'd be a different curve if it was 1 hertz and a different curve if it was 30 hertz, something like that. And then notice it's a log scale. And on the abscissa, this is the load. In other words, an earthquake with 0.2 G is here, spectral acceleration, and an earthquake with 1 G is here, earthquake with 3 G is here. And here is the annual probability that you'll get that motion. Now I want to point out something. Look at the mean curve, it's the black one. Okay? Well, at this particular site, at about a half a G, that comes around every few hundred years, or a few times 10 minus 3 per year. Whereas 2G comes around, this is the mean curve, comes around 10 minus 4 per year. Okay? And it's very steep. But the crucial property of this thing, besides it's very steep, is the uncertainty. If you ask, what's the likelihood of a 1G 10 hertz earthquake? Between the 5% and the 95 is more than a factor of 10. See it? And out here it's even more. So even though we don't know it very well, we know it, that's really a remarkably good knowledge, even though it's a factor of 10. I want you to remember that factor of 10, I'm going to come back to it. Now, on the other hand, if you look at the 10 minus 4 per year earthquake, that's the one that comes around every 10,000 years if it's stationary. Well, the 5% is 1G and the 95 is, 4G. This, by the way, is a western site, like in California. The eastern sites is much lower, but the same sort of spread. And what I'm showing you here is after all of that work I told you, the load at the site, typical hazard curve, that's the best state of knowledge. It's plus or minus a factor of something that works out about a factor of 10 and even more in the other direction. And that's the best we know. So of course, if you want to have high confidence, you've got to design your thing, not for the mean, but for the 90-something percentile, so as to have high confidence. And that's the way these things are done, and I'm going to explain that next. That's a typical site in the west. Here's a typical site in the east. It doesn't have all those different curves, but you see a typical site in the east, about 1,000 is 1G. I mean, it's 900 or something. But no, it's about a half a G is 10 minus 5, whereas the other one, the half a G, was 10 minus 4. But it still has this large spread, even more in the east, because they don't have earthquakes very much and not much is known compared to California. It could be plus or minus a factor of 10 in this direction. Okay? So these things are not known very well, but it's the best that the seismologists and the geologists can do. And that turns out to be the input for the rest of the analysis. Because if you want to have high confidence, you're going to want to use the high confidence curves. And I could have a whole lecture about how all this is developed, but I haven't got the time for that. I have one more curve to show. This is the frequency spectrum in which this is 10 hertz, and that's 1 hertz, and that's 30 hertz. That's the frequency of the motion. And for a typical earthquake, a 10 minus 4 earthquake, for example, it looks like this. There's a lot more between, let's say, 3 and 10 hertz than there is down here. And there's less going down into the long period, short duration earthquakes too. And there you can see this is what we call a kind of a uniform hazard spectrum. And you can see the 10 minus 3 curve. It peaks at about 1G at this particular site. 10 minus 4 curve peaks at around 1.8, and the other one's higher than 2G. And this energy, this spectral energy, is what goes into let's say, an electrical switch yard. Then the switch yard has to know that it's sensitive to 15 hertz, whereas the containment building is sensitive at 1 or 2 hertz. So that all has to get folded into the analysis that I'm going to talk about next. Okay? I have to move on. I said I'd spend a whole lecture just on that. But now let's talk about an individual item. An individual item. Some items are done by analysis. I'll talk about that next. But for many items, the only real understanding that helps us get our arms around this problem is by test, or in some cases by going and looking at real earthquakes. A big earthquake in Turkey, you can go and look. You see similar equipment and see at It's 10 of them. It survived this motion and it didn't survive this motion, and it tells you about where the issues are. And survive means to be able to perform its function afterwards. Survival means perform your function afterwards. Just remember that. The pump has to pump. The tank has to hold the water. The shear wall has to be able to hold what's attached to it. Okay? So for much of this stuff, the way we know how strong it is or how weak it is by test in shaker tables. Or, in some cases, a lot of experience from real earthquake data. You go and look out in the field after a big earthquake. But for electrical equipment, such as pumps, control systems and valves and cabinets and heat exchangers, you can't do analysis sensibly. We have a lot of tests. And then, if something's similar but not exactly like the test, it's an approximation, you have a little more uncertainty. But you ought to know that there are thousands and thousands of individual items being tested by the nuclear industry on these big shaker tables. And I'm going to show you a picture of a big shaker table just to show you how big they are. That's a shaker table big enough to take a 4-story building. And it can be shaken at earthquakes, very big earthquakes. It's an amazingly huge shaker table. Many of them are much smaller than that because they don't have to be as big as that. But that's just an example of the sort of thing that we have and for which we have a whole lot of data. Let me go back. So we develop data by shaking. You shake and it's okay, and then you shake again and it isn't, and you figure out at what amplitude of motion or what duration or what frequencies the thing fails to perform its function. Now there's also, as I said, oops, hold on. There we are. There's also earthquake experience data. This is not a nuclear plant, but the tanks are similar. This is a refinery. And I want you just to imagine they had a big earthquake at this refinery, and you can go out and look, and you can see that sloshing caused this problem of buckling, and the thing actually lost its integrity, and the water doesn't stay inside anymore. Then you go to another tank, and it's fine. Either it's stronger, or the motion was less, and you can figure that out. This earthquake experience data, supplemented by, oops. I lost it. How do I go for that? Oh, there it is. I don't know how to. Guess what? I can't figure out how to go to the next slide. Page up. There we are. I got it. Okay? For some things, we do it by analysis. Here's the bottom. The top I showed before. Structures and tanks and piping are done by analysis. You can analyze piping. Mechanical engineers know how to do that. But even the things that are done by analysis are benchmarked against shaker table tests too, so that we have a real experience in order to understand exactly how all that works. But it's mostly earthquake experience and some analysis that tells us how an individual structure or an item or an electrical thing or a pump or something is going to behave against earthquakes. Now, the way we do this is to, and there it is. Oops. I was here. Oops. I've got to go back. I don't know why it's moving forward, but I don't have to know. So, that's where I was. So let me go to the next slide. The way these designs are done are that there are industry codes. By the way, there are industry codes for non-nuclear. There's an industry code for electrical systems, and there are industry codes for tanks. But there are nuclear industry codes that have more severe requirements or sometimes special extra review and so on. And the codes by which these large nuclear power plants are designed use, well, for civil engineers, it's an ASE, that's a Civil Engineering Society. For tanks, it's the ASME, the Society of Mechanical Engineers. IEEE for the electrical stuff. They each have codes for how you design. There's an electrical code for how you design for seismic for DC buses, and there's another one for transformers, and that sort of thing. And for concrete, the American Concrete Institute and the like. These codes, which are then under an umbrella, under the American Nuclear Society, an overall umbrella code, are what the engineer uses to do the design. But when they do the design in detail for whatever the configuration happens to be, they're using the benchmarks from those shaker table tests to know how strong it's got to be for their site, and therefore how much extra margin or how much they have to embed in the codes. Now, when you're done for an individual item, imagine you did the design, then what the engineers do, and what is crucial to this analysis, is develop something which we call a fragility curve. A fragility curve has on the abscissa the load, and on the other axis, the ordinate, oops, there we are. The other one, that's the probability of failure. Now this is unrealistic. There's no fragility curve in the world that looks like this. But if it did, notice, and this is probability of failure. It didn't fail at point 2, and it didn't fail at point 3, and it didn't fail at point 4. But at point 6, it's all failed. Okay, you know, just a little bit more, and then they all fail. That's a typical fragility curve in your mind. There's no fragility curve like that anywhere. There's much, much more uncertainty. And I'm going to show you. There it is. Oops. No, I don't know why I'm skipping slides all the time. I don't know why I'm skipping slides. I just don't know. So I'm just going to go down here till I find it again. There. Now the next one, this is a more realistic fragility curve. This happens to be an electrical system, but they're all pretty similar to this. You put these on a shaker table, but you don't put one on, you put 30 of them on. They're identical. Some of them fail at 0.2 G, and some of them are still working at 0.7. This is the probability of failure if you have a family of them, and it's very, very broad, which means that if you want to have high confidence that this thing is going to be okay, you'd better make sure this thing is strong enough so it's up here or something, so that even way down here, the probability of failure is only 1% or 2, rather than design it for 0.5 G, and then half of them are going to fail. Why is this such a broad distribution? The answer is very complex, but I can tell you that if you put 20 identical transformers on a shaker table, off the same manufacturer, same, everything about them is the same, and you shake them, you're going to get a distribution that looks something like this. A very broad distribution in which the first ones fail at a pretty low, and some of them survive to pretty high input energy. This is peak ground acceleration, whatever the abscissa happens to be. And the reason for that is there's just one heck of a lot of variability in the things that cause this thing. By the way, it's not a collapse, remember, it has to perform its safety function. It's a pump, maybe the shaft gets just slightly out of line. Or if it's an electrical system, you might get a short circuit, and the other one doesn't get a short circuit because there's a 2 millimeters difference in the arcing or something. What I'm saying to you is that the typical fragility curve with which we do our analysis looks like that, with a whole lot of uncertainty, I'll call it, which is manifest of the underlying variability from one to the next. There's just one heck of a lot of variability. The second reason why there's variability is that this axis is called peak ground acceleration, but there are very different, this is a 0.5 G earthquake, okay? But some 0.5 G earthquakes are 20 seconds long and some are 10 seconds long, right? And yet we only have, the one figure of merit, not this complexity. And some have more different frequency spectrum and stuff like that. So there's if you fold that all in, you just get one heck of a lot of variability, and it's the way the world is. And it is this for an individual item, coupled with this hazard curve here, this thing here, and this, that then you have to use, that's for an individual item, you have to use those together in order to understand the probability of the failure of that one item. So let me go to the next slide, and then I'm going to keep going here. Now, for a typical nuclear power plant item, a single item, pump, a valve, shear wall, tank, the typical design input loading that is chosen by the Nuclear Regulatory Commission's regulations, and it varies from site to site, and there's some other variability, is an earthquake around 10 minus 4 per year. That's the likelihood, or it's maybe, if it were stationary Poisson, comes around every 10,000 years. But the typical outcome is that the target for how they end up is around 10 minus 5 per year for an individual item. And the reason for that is because those codes I told you about have a whole lot of conservatism in them. Put in by the engineers, the electrical, mechanical, civil, steel. They have a whole lot of conservatism. And what that means is if you choose as your design input loading for the codes, this 10 minus 4 earthquake, you're going to end up with high confidence that gadget is going to withstand about 2 times the load, okay, and still perform the safety function, 5 or 10, which is why what I said is what I said. Now, there's a lot of uncertainty that I mentioned before, the variability in the earthquake loading for the same earthquake. There's item-to-item variability, and you have to take that into account when you do all this, and the engineers do. But in the end, for a single item, if you want to do the arithmetic, you take the hazard curve, and this is the load, and you do a convolution with a Joni curve. Right? At 0.3G, the probability is 10%, and at 0.5G, the probability is 40%, and at 0.7G, the probability is 7%. You do this convolution. It's an arithmetic convolution that you can understand yourself. After all, you're engineers. And that convolution gives you, gives you the best estimate, but then there's all this uncertainty you have to put into, which then ends up with an uncertainty in the final line. But the seismic risk, which I said is expressed as the frequency of the seismic cause failure, is a convolution of these two. And that then, you can work it out if you do the two of them. For something like this, it might be 3 times 10 minus 5 per year is the probability that that gadget is not going to survive at that site when you take all the different earthquakes and everything together, and then you look at all the uncertainties. Okay? Now, one gadget does not make a nuclear accident, right? It takes several. So, of course, this is not the risk of a core damage accident. This is the risk of one item. You do the facility as a whole, here it is. To understand the facility as a whole, you have to do what we call PRA. You have to identify all of the accident sequences that matter. In accident sequences, you have the initiating event. In this case, it's an earthquake. And then you might have failure A and failure B and failure C. 3 different things have to fail before the accident sequence becomes a core damage accident. And maybe B is a human error, something like that, not a equipment failure as a function of the size of the earthquake. But in the end, you end up with a whole bunch of accident sequences, each one of which has been identified, and PRA has done that, identified the accident sequences that then could lead to what is the undesired endpoint, which is the core damage event, which then has a frequency. So let me go on. The top is the same. This is just a little bit of history, and you students aren't old enough, but I can tell you it was really rough at the time. In the 1970s, when this analysis had been thought about but not performed, many, many engineers, in fact more than most, thought this analysis was impossible. It's PRA. They didn't think that it was possible to identify all the accident sequences. And they didn't think that even if you did, you could identify the failures and the likelihood of the failure as a function of the load. And then they didn't think that you could identify how this earthquake and the load got from the earthquake to the site and then into the structure. It was just too complicated, and it was. But it took about 20 years from the, I would say, late 70s until the middle 90s before a whole lot of these analyses had been done and reviewed by dozens of people all around the world. And everybody agreed that the methodology was sound. It is now routinely used. There's an international standard that is under the auspices of the American Society of Mechanical Engineers and the American Nuclear Society. It's a standard for how you do this analysis. A PRA standard for seismic PRA. It has 60 or 70 requirements. You do this, and you do this, and you do this, and you don't do that, and you do this, and you do this. And if you meet that standard, you're going to have a solid analysis. But that took a long time, because by the time the standard was written, I'm guessing it was early, well, I know, it was 2002. But the first of these analyses were done in the late 70s. So what is that? That's 35 years. And the reason I know about that standard, by the way, is that the first seismic PRA standard was done by a committee that I chaired. So I was right in the thick of that and know a lot about it. Now, let me go back. Now we do this analysis routinely. You'll go to a nuclear power plant down the coast of Diablo Canyon, but you could be anywhere in the world. And I'm going to tell you how it came out. It's not always the same. They vary a lot. But at a typical nuclear power plant, there are 5 or 10 important sequences and dozens of them that aren't important. They're either not important because the probability of getting into trouble is lower, or the consequences are modest. But for the ones that have a reasonable probability, and reasonable, 1 10 minus 5 or something, and have consequences that are of concern, every plant has 5 or 10, and they differ from one plant to the next, although there's some similarities because certain things For example, when we began this, batteries and battery racks were vulnerable, and then everybody fixed them, and now they aren't. That sort of thing. But when you do this analysis of a typical plant, an individual sequence is typically around 10 minus 5 per year, or a little less. Right? The total accident frequency is 5 or 10 times that. It's several times 10 minus 5 per year. But most of those sequences initiated by an earthquake don't cause a large release. They cause trouble. The core damage, like 3 Mile Island, core damage, hardly any release. The large release frequency is about a factor of 10 lower, several 10 minus 6 per year, and that's typical. There's a lot of variability from one plant to the next, but that's the typical way that it comes out. And at the end of this, for a facility as a whole, like a big plant. Now, why do we have confidence? Let me explain. There's lots of experience analyzing and testing individual items, pumps, valves, tanks, shear walls, electrical buses, that sort of thing. Got a lot of experience with that at shaker tables and with individual earthquakes that happen. There are over 100 nuclear plants around the world that have been analyzed, and by a few hundred people. There's a community, and I'm part of it, and that community review each other's stuff. And those reviews, plus validating against analysis and earthquake experience, have led the community to have confidence in these results, even though the uncertainties can be a factor of 10. I showed you between the 5 and the 95 just on the hazards, a whole factor of 10. So you have to take that into account. When I said up here, I said, a typical, that's our best estimate or our mean value, but it could be a factor of 3 or 4 higher, a factor of 3 or 4 lower in a real case. We don't know what the reality is, you just don't know. And it wouldn't surprise people if that was how it is, because those uncertainties are what they are. And we try to reduce them, but they are what they are. Now, I just said this before, I'm going to say it again. How likely is a major core damage accident arising from an earthquake? And I said we have over 100 analyses, and the typical core damage frequency is several 10 to the minus 5 per year. Large release, several 10 minus 6 per year. And that's our best knowledge, but those uncertainties are what they are. Now I'm going to come to something really important for you, okay? First, our community has confidence that we understand these things. But I want you to read this last bullet. It's my last bullet in the talk. Whether that outcome is safe enough is not something I've talked about. That's for you to decide. You might decide it is, and you might decide it isn't. The French might decide it is, and the Australians might decide it isn't. These are societal judgments as to whether that outcome that I showed you is safe enough. Okay? I'm describing our analysis that provides the state of knowledge we have about these things with its uncertainties. And whether that's safe enough is an individual decision or a societal decision. Now, the NRC has told us in their safety goal policy statement and a lot of other things that the range like this is acceptable for seismic safety at the nuclear power plants in the U.S. The NRC has said that's safe enough. Okay? But there are people that don't think it's safe enough, and that's not a dishonorable, it's just plain a difference of opinion about how much risk you want to run and what other risk you want. That's okay. I don't have any problem with people making different judgments, providing they're being honorable and direct about what they're basing it on. But the typical nuclear power plant accident frequencies in this range of about 10 minus 5 per year, that's the mean value, and as I said, it could be higher or lower by some factor, is how we've come out. And I believe that with the knowledge we've developed in this community over the last 30, 40 years, that we have really high confidence that that range is about right. Within, that if somebody says, no, it's a factor of 50 higher, no, I don't think so. That wouldn't be supported by the evidence. And then there's some people who say, well, no, it's 10 minus 7. No, that's not supported by the evidence either. It's in this range. We don't know more than that, but we really do know that. Okay? And it's nice to be able to say that, because there was a time when I was a student and then a postdoc and just starting out, when frankly we didn't know that. Nobody knew. The industry used to say core damage accidents are impossible instead of something like that. And people who were opposed to the plants but didn't know anymore anyway said, oh, no, they're going to come around every 100 years. And that's just not true. I mean, for one plant. It's just not so. So that's the end of the talk. I'm done with my explanation. I'd be happy to take whatever questions you might have about this. Just go ahead and shoot.
Bob, I have two questions. Number one.
By the way, Howard Lambert's one of the collaborators that I've worked with for the longest time. I mean, going all the way back to the 80s. We got 40 years of working together on this, that, and something else.
So the question was planted. That's
No, believe me. I have two questions. Number one, how is different manufacturers treated in the shaker test? Do you know, like relays?
It's done by model number.
Oh, so you
yes.
have different pumps and different valves and different relays?
If you've got a transformer, Westinghouse might have 9 models. General Electric have 7 models.
Yeah.
It's got to be done by model number. You can't, there's too much variability for that not to be so.
So you do it for every model number?
Yes, you do.
Oh, wow, I didn't know that.
Yeah, by the way, there's thousands of tests, okay?
Wow.
Okay.
The other comment that I have that when I was involved with, you were talking about human error,
Yeah.
and also random failures are important.
Yes.
When you lose offsite power, you consider your diesel generator starting.
That's
and it's
correct.
not only due to earthquake effects,
Absolutely.
but due to random, and that's also part of the PRA that's important too.
That's right. Let me go to this slide. When I said A and B and C,
Yeah.
B might be a random failure that was failed, even though maybe it's been sitting there for a week, failed, and you didn't know it, and then the earthquake comes along, it's been failed. The regular PRA takes account of that too. Or it might be a human error. Typically, if you want to know the rough numbers, maybe 20 or 30% of our sequences, the seismic sequences, have a random failure or a human error. And then the others, 80, 70, whatever it is, percent, all the failures are earthquake. Okay. But those non-seismic failures and human errors are part of the sequences, and some of them can be important. Yes, thank you.
I have 2 questions. Does the codes for nuclear power plants prioritize the integrity of the building of the power plant over the safety of the workers during an earthquake?
Oh, boy, is that a good question. The design is designed for the safety of the plant against releases. Okay? Okay? The design for safety of the workers has a different envelope, and that turns out to be a lesser challenge than the other design for earthquakes. You can just, if you sit down and write down sequences that might harm a worker but don't cause a large release, they turn out to be less common and less consequences, almost always. Occasionally you'll find one and then it's in there, but not mostly, which is nice to know if you're a worker.
And the other one, do these analyses consider subsequent events like fires or tsunamis?
An earthquake-caused fire is in there because you can get a fire from a short circuit, okay? There is no analysis like this that contemplates what happened in Fukushima with the tsunami. Let me describe. It's easy. It was in March of 2011, and there was a huge earthquake, 100 kilometers offshore, maybe a little more, and it caused a tsunami. Now, when the ground motion from that earthquake got to the shore, which took, by the way, only a minute, this is fast, it was the largest earthquake in Japan since instruments were installed. Okay? There had never been an earthquake that big, and it shook all sorts of things and caused a lot of trouble in the nearby towns, even though it was 100 kilometers from the source. But the nuclear power plants, and there were 3 of them nearby, like 8 or 9. Fukushima had 4 units, and
6 units.
And Daiichi had 3, and then Onagawa had it. Anyway, they all survived the earthquake without hardly any trouble, and there certainly wasn't any big accident surviving that earthquake. They survived the earthquake great. And if you're an earthquake engineer, you're feeling really good about that. But then, an hour later, whatever it was, the water came. Okay? And that analysis is done separately. after all, at Fukushima, when the water came, the plant was intact. It had been shut down actually for an hour or whatever it was. And it was the water that did them in. And that analysis is done separately, okay? You could couple it, but I don't remember anybody has done that. Now, the Fukushima accident, there was a whole lot of trouble there. It's hard to go looking at the Fukushima plants and try to figure out what failed and what didn't. But you can go next door to Onagawa or just up the road to Daini, and those plants are intact. They were fine. And you can inspect them. And in Onagawa, there was essentially no earthquake trouble at all. Well, with one trouble. They all lost offsite power because the grid was vulnerable. But the plant was designed for that. Everything was fine. And they were all okay. It's nice to be able to say that if you're an earthquake engineer doing this stuff, they were feeling good about that. Of course, you feel awful because the tsunami is what did them in. Okay.
Yeah, actually, the question I want to ask is about tsunami, the earthquake-induced consequence. You have an explanation in there. But why is not coupled? You know, in the case of Japan, when earthquake-induced tsunami is so well known. So even earthquake is not a problem for the plant. But the tsunami certainly comes in, and really actually in Onagawa is the seawater pump.
Yeah, that's right.
The
That's right.
tank that saved the plant.
Well,
In Daini, 4 units, 3 of the seawater pump were washed away.
Yeah.
So 1 is still operating,
But they-
and the plant was saved
but
because
they make-
that one saved them. But
all right, so I know the answer to which I'll tell you.
Daiichi,
Nobody had done that analysis before anywhere.
so this is something new that we have, as an engineer, you have to look into.
Joshan, 3 or 4 sites around the world have done that coupled analysis.
Yeah,
All right?
but not in Fukushima.
Well, I don't think so. And the extra insights aren't really very exciting because it's the sort of thing that you kind of knew. Okay, although it does, when it jumps off the page in an analysis, it's better than just sort of kind of knew. But it wasn't like there's some remarkable new insights, which
So
is,
PRA will not discover that. I mean, will not point out
Well,
there
it
is a
could-
missing link somewhere.
it could, but you have to structure the analysis in a way that makes it so, and people haven't done that, okay? All right? Of course it could, right? You'd have to work out a coupled probability, and that's doable.
So, at that time,
Gary Johnson.
they were considering increasing the flood levels before Fukushima happened. Would that have actually caused anything useful? Because the problem was over here.
Probably not. Probably not.
For DOE sites such as the Plutonium Production Facility at Lanel, and then criticality safety standards specifically, they call out that safety engineers don't have to analyze for smart events as a result of earthquakes.
Yes,
I was
yes.
wondering if you had any thoughts on that.
Yes, actually, maybe you can explain what you mean by a smart event. Yes, I've actually been involved with some of that at Los Alamos and also at Savannah River.
Yeah, so I guess smart events are if you want to cut costs and don't want to credit your glove box for surviving an earthquake, you can just say, well, everything is just going to go everywhere, and the likelihood that your mass is going to assemble into a criticality accident possible geometry is negligible. So I guess what are your thoughts?
The earthquake-caused criticality configurations have been analyzed in a few of those places where it matters, but it's not universally done.
Yeah, we did that in
You did it at Livermore.
Budnitz facility.
Yes, they did that at Livermore.
Do you have
And they did it at Los Alamos in that, whatever that building is called.
thoughts about whether it should be doing, whether
Whether-
they should be analyzing for those hazards?
Well, somebody has to do an approximate analysis that would justify that there's a risk big enough to do an elaborate analysis. And I know they've done it at Savannah River, and I know they've done it, and they did it at Y12 at Oak Ridge, and also at Livermore.
And PF4?
Yeah, okay. So the approximate analysis, we better spend a lot digging into that. But I'm not sure that that's been done very many other places.
I think we have another couple of questions.
Yeah, it's not clear to me what is considered an accident. There must be some level of damage done above that as accident, and then there are several levels of it.
The end point for the nuclear power plant analysis